Suppose I have a collision where a truck hits a Volvo, or maybe I could say a Volvo hits a truck, and during that collision, if I were to ask you to find the total impulse for the truck-Volvo system, well, impulse is a force times a time. And if I want the impulse on the system of the truck and the Volvo, I would have to find the impulse on the truck as a vector and the impulse on the Volvo as a vector and add those together. Well, forces require three body diagrams. The truck and the Volvo have weight down and normal up, and then I have a normal force by the Volvo on the truck during the collision, and a much bigger force by the truck on the Volvo because the Volvo has more mass. Because the Volvo was did I say the Volvo has more mass? That's not right. The truck has more mass. So is that okay? The truck was speeding. The truck was speeding and has more mass. No? No. They have to be exactly the same by what law? By third law. And folks, that is the very foundation of rocket science, Newton's third law. Without Newton's third law, we don't have conservation of momentum. And that's what rocket science is built on. Okay? Watch how it happens. The impulse on the truck is just the net force on the truck times the time during which it experiences that force. The impulse on the Volvo is just the net force on the Volvo times the time that it experiences that force. Now, I think we can agree that if this collision lasts a tenth of a second for the truck, it also lasted a tenth of a second for the Volvo, so we can get rid of those indices. Now, here's the thing. This vector is the same as that vector, only in the opposite direction. And so when I add these together, I always get 0. Now, impulse is what changes momentum. If my system has no impulse, what does that tell me about the change in momentum for that system? It doesn't change. And that's what we mean when we say it is conserved. It is conserved. Here's my promise to you. If you will always, always, always include everything that collides, or hits, or pounds, or touches, or pushes, anything that interacts in your system, if you do that, then all of the forces will come as equal and opposite pairs by Newton's third law. The impulse on that system will be 0. If the impulse is 0, that means rather than going to the general equation, you can go here. Whereby P initial equals P final, I mean the momentum of the system initial equals the momentum of the system final. Now there's a caveat that's important. When you were dealing with energy, you got to choose what you meant by initial. You got to choose what you meant by final. They could be any time during the day. But when you are using momentum on a collision, you don't have that freedom. Initial means right before the collision. Final means right after the collision. You can't wait for those cars to slide across the pavement and into someone's garden. It's right after the collision. Right after. Now, that is always, always, always conserved. In every single collision, momentum is always conserved. Even if that collision involves C4. No matter how messy the collision is, it will always, always be conserved. Now,